In today's lecture, we are going to talk about water and how water moves through plants. We're going to start by reviewing some properties of water that we've talked about before, like polarity, as well as cohesion and adhesion. We then are going to talk about the processes of diffusion and osmosis. Diffusion is when dissolved substances move from areas of high concentration to lower concentration. Osmosis is when water moves from areas with lower concentrations of solutes to areas with higher concentrations. We'll go over that in much more depth. We're then going to talk about the importance of osmosis in controlling the opening of stomata. These were the openings on plant leaves that we talked about when we talked about leaves earlier in the semester. We're going to talk about water movement through the phloem and what powers it. We will also talk about what powers water movement through the xylem. To return to a subject we talked about a couple lectures previously, water is polar. And what this meant was that the oxygen and hydrogen atoms in water share electrons. In other words, there's a bond that connects them. However, oxygen is able to pull more strongly on the shared electrons than are the hydrogen atoms. So while these are sharing electrons, the electrons are hanging out closer to this end of the molecule and further away from this end of the molecule. Because electrons have a negative charge, that means this end of the molecule has a slight negative charge. And because the electrons are not close to this side of the molecule has a slight positive charge. And essentially then, a water molecule is analogous to a very weak magnet. And this is important because, as you know, different poles of magnets attract each other. So the positive end of a magnet would attract the negative end of a different magnet. The same thing is true in a water molecule. The positive side, so the hydrogen side of this water molecule, is attracting the oxygen side, or the negative side, of these neighboring water molecules. And the same is happening here in reverse. And so essentially, these water molecules have a tendency to stick together. The property of like things sticking together, in this case, they are like because they are all water molecules. This property is called cohesion. Cohesion then is the attractiveness between molecules of the same type, and it leads the water molecules to stick together. We can also define a similar property, adhesion, which refers to attractiveness between different kinds of molecules. So there are other molecules besides water that have polarity, and water is going to be attracted to those, or it will adhere to them. We also previously talked about the fact that water dissolves ions as well as other polar substances. And remember that ions are charged atoms. Because they are charged, then water, which has partial positive and negative charges, is going to like to stick to them in the same way that magnets would be attracted to one another. And so we saw that the negatively charged ion, like this one here, is going to attract the hydrogen sides of water molecules, and the positively charged ion, like this one here, is going to attract the oxygen side of water molecules. Because these attractions are energetically favorable, if we take something like, let's say, sodium chloride or salt and put it into water, it is going to dissolve in order to allow the water molecules to form these rings around each of the ions. So the important thing here is that both ions and other polar substances like sugar are going to be able to dissolve into water. So we've just said that substances can dissolve into water. Let's imagine we take this solid and we put it into the water and it starts to dissolve. Initially, we're going to have a high concentration then of the cations and the anions where that block of solid salt was before. However, over time, that is going to spread out. And the spreading out of ions that dissolve, or the spreading out of polar substances dissolved in water, is going to result by a process called diffusion. And diffusion occurs because there's always random movements of molecules. So even in a solid, there is going to be slight movement of molecules, or of atoms. However, in a liquid or a gas, then molecules are going to be moving around much more. They move around a lot in liquids, and this says solids, but let's change that to gas. In a gas, they're going to move around even more than in liquids. And so as these molecules are moving around, they're bouncing into each other. And each time they bounce off, they're going to go in a new direction. On average, if we look at what happens as a result of many of those bounces, there's going to be a general tendency to bounce away from areas where there are the highest concentrations and to bounce into the areas where there are lower concentrations of the dissolved substance. Because molecules are on average bouncing away from areas of high concentration, over time we are going to see that the results are a net movement from areas of high concentration to areas of lower concentration of that substance. And this is what that would look like in the diagram. Initially, we have all of the molecules together. Over time, they are going to be approximately equally spread out, or at least randomly spread out in the solution. This same process can happen if we have two containers that are divided by a semi-permeable membrane. Semi-permeable means that some things are able to get through. It is permeable to them, but other things are unable to get through. It is impermeable to those other things. In this example, the dissolved substance indicated by the red dots is able to go through the membrane, so this membrane is permeable to it. As a result, we have over time the substance spread out until it is in a similar concentration on both sides of the membrane. This is a simple example of diffusion. Diffusion is going to be important for our purposes because it occurs in plant cells. Plant cells, like animal cells too, are going to be divided by a membrane. And that membrane is going to have the property of being semi-permeable. So what we're looking at here is one cell at 3 different times. Initially, at time 0, we have a whole bunch of some substance outside of the cell and none of that substance inside the cell. However, over time, we see what happens. At first, a few of those molecules get through, and then, given enough time, we're going to have a similar concentration of this molecule inside the cell as we do outside of the cell. Now, if this molecule was not permeable through the cell membrane, then this wouldn't happen. Instead, even after a long amount of time, we would still have the substance outside and none of the substance inside. It turns out that for many molecules, they are not very good at crossing the plasma membrane. However, water has some specialized openings where it is able to go through the membrane. So we can say that the membrane is differentially permeable, and water is one of the things that is able to get across. We've talked previously about diffusion, where we said that dissolved substances move from areas of high concentration to areas of low concentration. But what we need to think about now is what happens if that substance is not able to cross the membrane because the membrane is not permeable to it. However, water is able to cross the membrane because the membrane is permeable to water. When this is the case, then the process we need to be concerned about is called osmosis. And osmosis refers to when water molecules move from an area with less of a dissolved substance, so for example over here, towards areas with higher concentrations of the dissolved substance, like over here. So if we initially had low concentrations and high concentrations, and the substance could not go through the membrane, then after enough time, we would see that the water would move across to the other side as it has moved from an area of less dissolved substance towards the area with more. Notice that this has a very similar effect as diffusion. In diffusion, we ended up with similar concentrations of the dissolved substance in both areas, and with osmosis we do too. The only difference is that with osmosis, it's the water that is moving to get the same concentration on both sides, instead of the substance itself moving. Osmosis is going to be really important for controlling the water level in cells, and as a result, we'll see it controls how water moves throughout a plant. We'll think about this first, thinking about what happens with individual cells, and we will consider three scenarios. In the first scenario, let us imagine that we have a lot of a dissolved substance outside of our cell, and we don't have very much of it inside. We have just a little bit. In this case, because of osmosis, one more assumption, let's assume that this dissolved substance does not cross the cell membrane very effectively. So it's pretty much stuck out here. In this case, then, because the substance cannot move into the cell, instead, by osmosis, we are going to have water leave the cell, and the cell is this yellow area. However, most of the water has left and moved out here to dilute this substance. The result is that there's not very much water left inside our cell, and the cell has gotten very small. Cell walls cannot change size very easily, and so what's happened is the cell itself has pulled away from the cell wall, causing it to have this funny shape. Incidentally, when this actually happens to a living plant cell, it does usually kill it. So this situation would be dire for the plant. Even before the cell dies, as water leaves the cell, then the cell wall, or rather the cell membrane, is not going to be pushing very hard against the cell wall. It is the push of the water in the cell against the cell wall that makes the cell rigid. This means that when the water leaves the cell, as pictured here, there's nothing pushing against the cell wall, and it's not going to be strong enough to hold itself up. This is going to cause the cell to become flaccid, which is a synonym of limp. Let's now consider what happens in the reverse situation. Let's imagine that this substance is at a very high concentration inside the cell, and there's not very much of it outside of the cell. Again, let's also imagine that the substance cannot cross the plasma membrane. In this case, then, because of osmosis, water is going to move from outside of the cell into the cell. This is going to continue until the cell reaches its maximum volume, and you can see that the cell walls here are now pushed outward. This is going to cause the cell to become stiff, very much like if you filled a balloon with water, the balloon would become stiff as you filled it. And when the cell is stiff, we can refer to it as being turgid, which is a synonym. For the sake of completeness, we can also think about a situation where the concentration of the substance is similar outside of the cell to inside of the cell. In this case, there will still be water movement from inside the cell to outside, but there will also be water movement from outside of the cell to inside. This will just be random movement in both directions. However, since the concentrations are similar on both sides, there will not be any net change in the amount of water inside the cell. So the cell will not proceed to get more full and more turgid, and it will also not proceed to get less full and become flaccid. It will just stay the same. Cell turgidity is important because it is what provides support for the entire plant. And I used the balloon analogy before, but think of it again. If you have an empty balloon, it is going to be limp. But if you have a full balloon, it is going to become increasingly stiff. That means that a plant with abundant water is going to have a stem that stays rigid and leaves that can stay rigid. The stem here is probably reinforced with other material too, and so the stem wouldn't necessarily fall, but you can see that the leaves are being held up, and that is done almost exclusively by the force of water against cell walls. We can also think about what happens if a plant loses water. As water is lost from plant leaves, then there's no longer going to be a push of that water against the cell wall, and as a result, those individual cells will become flaccid. The leaf as a whole will wilt, and wilt refers to this droopiness caused by a lack of water. You may have seen this already this semester in your coleus plants. Hopefully not, but it tends to happen to all of us. Eventually we forget to water plants, and initially the leaves droop a little bit, and then they droop more and more. There is some point at which the leaves are so short on water that the individual cells resemble this. The cell has pulled away from the cell wall and the cells have died. That is the point where the plant will no longer be able to recover, even if you add more water to the soil. But if the leaves have just gotten to this stage of not having higher or lower solute concentrations inside and outside of the cells, then they might get a little bit droopy, but they will be able to recover. The next topic that we are going to talk about is how plants control their water loss through stomata. Remember, stomata were these openings like right here on the underside of leaves that we talked about in the leaf unit. And we said these openings can open or closed. So this is what it looks like when it's closed, there's no opening. There are two guard cells. That's this cell here and this cell here that surround the openings. It turns out that whether those openings are open or closed is going to depend on the amount of water in the cells and hence the turgidity of the cells. So let's first think about what happens when plants have good conditions. So they have abundant water and they have light and are able to photosynthesize. If this is the case, then the plant is going to actively send solutes into the guard cells. So what we see here in this light greenish yellow color is one guard cell and the second one. And we see these pink arrows indicating that this pink solute is getting moved from outside of the cells into the guard cells. This is going to be important because once the solute concentration gets high inside the guard cells, then we are going to get the movement of water represented by these blue arrows into the guard cells as well. In other words, these guard cells are going to swell up with water. Well, as they swell with water, they are going to expand. And because of the particular way that fibers are arranged in their cell walls, as they expand, it's going to create this opening, this black circle right here, and this is the opening through which air can pass. Now let's imagine that conditions get bad. Maybe it gets dark so the plant can no longer do photosynthesis, or maybe because there was this open stomata, there was a lot of water loss of water vapor that evaporated out of the opening, and now the plant does not have enough water. If either of those are the case, the plant needs to close its stomata, and this is how it will do it. It is going to send those substances back out of the guard cells, indicated by the pink arrows pointing outwards. And as a result, the concentration of substances in the guard cells will decrease. It will increase outside, and the result of this is that water is going to leave the guard cells. You can see that here and here. The guard cells will shrink, and as they shrink, this opening will close. So why do plants bother opening and closing stomata? Remember that open stomata allows photosynthesis to occur, which is a good thing, but it also allows water loss to occur, which is a bad thing. And conversely, closed stomata prevent photosynthesis but conserve water. So the plant opens and closes its stomata to balance these two countering benefits and losses. So we have now talked about how plants control whether or not their stomata are open, which in turn controls how much water they lose through their leaves. The next topic that we will talk about is how do plants use water to move sugars through the phloem. Let's go back. It's been a while since we talked about phloem. So let's remind ourselves that phloem is the part of the vascular tissue that transports mostly sugars and other organic molecules, like sometimes proteins and also things like vitamins. And so this is critically important that a plant be able to move things around. We said what phloem did earlier, but we haven't talked about how it actually moves these substances. Phloem moves sugars and other dissolved substances from source areas that have extra to sink areas that need them. For example, during the summer, the leaves of the carrot would be the source, and those leaves would be making sugar, which the plant would then move down into the carrot root, which would be the sink. The next year, when the carrot needed those sugars to make new leaves and flowers, then this would be reversed. At least in springtime, the carrot itself would be the source and the leaves would be the sink. We're now going to talk about exactly how the plant achieves that movement. And we'll start by how does the plant get substances inside, and then how does it move it? So what we have pictured here in green is a set of sieve tube cells. Remember, these are the cells that really are the conduits for movement in the phloem. The first thing that will happen is the sugars or other organic molecules are going to get moved into these sieve tube cells, and the plant needs to spend some energy to accomplish that. Here we can see those have now moved inside. This means now that there's a high concentration of substances inside the sieve tube cells compared to outside. Again, because of osmosis, this is going to cause water to move into this cell. And just like we said for other cells, this is going to cause swelling and an increase in pressure inside this cell. If pressure increases, then just think about squeezing water in a hose or in a balloon. If you increase pressure somewhere, then the water inside is going to move away from where you're squeezing. So here, there's a cap at this end, so it's going to have to move in this direction. As a result, the water is going to move this way, but because these substances are dissolved in the water, they're going to move too, and we're going to get movement of the substances in this direction through the phloem. This is the source, it's where the materials went in, and this will lead to a sink where the materials are needed. Here we can see then that the water has moved away from the source where it came in, and now these the dissolved substances are at the other end of the phloem. Perhaps this is a root during summertime. At this stage, the sugars or other dissolved substances are then transported out of the phloem where they are needed. here we can see the substances have been moved out. But now notice that the concentration of substances is higher outside of the sieve tube cell at this end than it is inside. As a result, by osmosis, water is going to leave this end of the phloem. If water leaves, then there's no longer going to be as much pressure pushing against these cell walls, and the pressure will have decreased. That means that out here at the source we have high pressure, down here at the sink we have low pressure, and the net difference in pressure is going to lead to that flow of water with dissolved substances from one end to the other end. The cool thing about this system is that it allows phloem to transport sugars and other organic material from sources to sinks without needing any coordination to do it. So there's no equivalent of a computer system that figures out where to send materials. It's simply that any part of the plant that has extra can move it into the phloem, any part of the plant that needs it can move it out, and depending on how great the ability to supply is and how great the need is, that is going to determine where in the plant the phloem moves. So the process of phloem movement is really based on where substances are loaded and where they are unloaded. That's going to result in a change in pressure that then determines the direction of flow. We've now talked about what controls stomata opening and closing, which controls water loss through leaves. We've talked about phloem and how the direction of flow through the phloem is determined. The last process we will talk about is transpiration. And transpiration is literally the process of water loss through the stomata of leaves. What we're going to see is that water in fact gets pulled upwards from the leaves, and then it gets pulled through the stems and it gets pulled through the roots. So if the process of moving water and substances through the phloem is a pushing process, the process of moving water through the xylem is going to be a pulling process. We will examine this process starting with what happens in the leaves, and then working our way backwards to what happens in the stem and roots, and finally the soil. So here we're going to start with what happens in a leaf. Let us imagine that the cell we're looking at here is a leaf cell, and it has some amount of dissolved substances in it. And let's imagine that this leaf that this cell is a part of has open stomata. As a result, there is water that is leaving from the leaf and even from this cell and escaping through the stomatal opening. So we have water that escapes the cell. If water escapes the cell, then what that is going to do is it's going to decrease the volume in the cell. Let's imagine though that the solutes in the cell can mostly not escape because the membrane is not permeable to them. That means that after a period of time of water loss, we are going to end up with a smaller volume inside the cell and the same amount of solutes. If that is the case, what we have effectively done is increase the solute concentration inside the cell. Same amount but smaller volume, and so it's a higher concentration. We already know though that because of osmosis, if we have a higher concentration of a substance, then that is going to tend to pull water from areas where there's lower concentrations of the substance. And if we think about the xylem, it's going to usually have a very low concentration of dissolved substances in it. So the upshot of this is that as water leaves the cell to evaporate away through the stomata, we are going to have that water replaced by water from the xylem. Remember, the xylem is the system of vasculature that primarily moves water as well as dissolved minerals. So water is moving from the xylem into this leaf cell. We're going to follow up with what happens to that on the next slide. Back at the start of this lecture, we reviewed what cohesion is, and here is why cohesion is important today. As water moves out of the xylem into that leaf cell, it is going to literally pull other water molecules behind it. And those water molecules that are getting pulled behind it are in turn connected to water molecules still further back. The result of all of this is that the xylem is going to pull water up in the leaves, through the stem, and through the roots. All of these water molecules are connected in one continuous chain the entire length of the plant. And if they get pulled right here, that results in a pull that goes all the way back to the roots. So xylem is an unbroken chain to the roots. That means that eventually water is going to get pulled from the roots. That water that's getting pulled from the roots has to get replenished, and that water will be replenished or replaced by pulling water out of the soil because the roots are in contact with the soil. So usually in at least well-watered plants, they will be able to pull water from the soil because there's an abundance of water there. But that's not always the case. If in fact it is the case, if soil is wet, then the water that leaves by transpiration and then all of the water that gets pulled from the roots gets replaced with this soil water. However, if the soil is dry, then any remaining water molecules that are in the soil are going to stick very tightly to soil particles. This stickiness is due to adhesion, or the attraction of polar particles to one another. And because the adhesion is very strong, at some point water or plants will not be able to pull any additional water molecules away. You can see the result of that here. This plant has gotten droopy because water that has been lost through its leaves has not been adequately replaced by the roots. Before the plant gets droopy, it will close its stomata to help prevent water loss. And remember, the leaves have a cuticle that also helps to prevent water loss. However, neither of those is perfect. Water is a small molecule, and it can find ways to escape, even through the cuticle. So eventually enough additional water will get lost that the cells will become flaccid and the leaves will wilt. This means that dry soil is one factor that can cause wilting. It's an obvious one, but there's a second way that we can cause plants to wilt that maybe is less obvious. That is that additions of substances like salt and fertilizer can actually cause wilting, and this is one of the several reasons it's important not to over-fertilize. So both salt and fertilizer are either made out of ions or polar substances, and that means they are both readily able to dissolve into water. Let's think about what this means. Here we have a simple diagram with one root cell and some amount of soil water that is up adjacent to this root cell. Let's first think about a situation where we have a fair amount of solutes inside the root cell, which is typical, and a lower concentration in the water that is outside of the root. In this situation, due to osmosis, water will move from the soil water into the root cell. But now let's think about what happens if we put extra fertilizer or salt into the water that we use to water a plant. Now we have increased the solute concentration outside of the root cell. We haven't changed it inside, it's still the same as it was. But because the concentration is now higher in the soil water than in the root cell, water is going to move from the root into the soil. The effect of this can be to cause root burn, and we'll look at that here. So here's a plant that was over-fertilized. And the result of this was that the roots were no longer able to take in additional water, and the plant leaves have wilted. Before they wilted, some additional damage was caused, which causes the brown coloration you see here. So just to emphasize this, when excessive dissolved substances occur in soil, then plants are going to lose their ability to take up water, with wilting and damage being the result. We have now talked about 3 different processes that are affected by properties of water. We talked about stomata, we talked about phloem, and we talked about xylem. Remember at the end of this that phloem is always going to be a push of substances through due to water pressure. Phloem is always going to be a pull of water upwards from the soil to the leaves due to the cohesiveness of water and the process of transpiration. So some final thoughts from today's lecture. First, for reasons that we've now talked about, it's important that plants closely regulate the amount of water in their cells. And they're going to do that sometimes by moving solutes in or moving solutes out. They are also going to open and close their stomata to control overall water availability. Additionally, during dry conditions, we sort of just said this, plants can close their stomata, which will help them save water. But remember, there's a trade-off. When they close their stomata, then they are going to be less able to photosynthesize. Something that we didn't talk about, but that your reading talks about, is that cell expansion also depends on water. That's because for cell walls to expand, what needs to happen is there has to be a large push against them, and that push actually comes from water coming into the cell and then the additional water pressure being the force that allows it. And finally, as a very practical matter, when wilting occurs, we know that our plants are lacking water, but it's not good to wait for a plant to wilt to water it. This is sort of when it is telling you that there's a problem. Instead, you should try to anticipate when the soil looks dry and make sure to water before this occurs. The next topic that we are going to talk about relates a little bit to the idea of salt and fertilizer in the soil. We are going to talk about plant mineral nutrition. So what are the requirements for plant growth and how do plants get those minerals?